Hello, in this video we'll discuss section 8.2 contour diagrams. Let's consider the graph of the surface z equals f of xy equals x squared plus y squared. This is a surface we looked at last time. It's known as a paraboloid and it looks something like this. If we slice the graph vertically, what do the slices look like? So let's kind of imagine setting this surface on a cutting board and bringing the blade down to get a vertical slice. We should think about how we want to position the surface on the cutting board. We could do it in such a way that we're slicing parallel to the x-axis, or we could position it such that we're slicing parallel to the y-axis. Let's first fix y equal to c and let x vary. I've indicated this in the second drawing here. Notice we're fixing y equal to c. So here's our constant c that we're fixing y to be, and we're letting x vary. So notice we're running parallel to the x-axis here. And what we could do is replace y with this constant c so that f of x comma y looks like this: x squared plus c squared. And if we choose a value for c, say c equal to 0, this reduces to x squared, and notice I've sketched the graph of x squared in the xz plane. Now we'll fix x equal to c and let y vary. So I've kind of indicated this in the second drawing. Here's x equals c, and we're letting y vary. So now we're running parallel to the y-axis, and what we could do is replace x with this constant c, and then f of x comma y is f of c comma y, which is equal to c squared plus y squared. And I've chosen a value for c. This time I chose c equals 1, so we'd be plotting 1 plus y squared, which would look like this, and it's in the YZ plane. If we go back to the graph of the surface, I think you can see that if you were to slice vertically, either parallel to the x-axis or the y-axis, you do end up getting a parabola. Let's shift gears a bit here. If we slice the graph horizontally now, what do the slices look like? So now we'd be fixing z, the output, equal to some constant c. Then f of xy equals x squared plus y squared is equal to c. And this should be an equation that looks familiar to you. That's the equation of a circle. We call such curves level curves or contours. Here's the graph of our surface once more. And if you picture slicing this thing horizontal, I think you can see that you would get a circle. In fact, slice the surface at the top of this box here, and you can see a circle. So let me move down here. This is a contour plot. This is showing us various contours. And notice they're all circles. We've got these concentric circles. The innermost circle, this dark blue circle, is a circle of radius 1, so that corresponds to c equal to 1. We'd have x squared plus y squared equals 1 to get this innermost contour. Let's look at another example. Sketch a contour diagram for the function at the bottom of the page, z equals f of xy equals y minus x squared, and we want to label at least 4 contours. So what you do is you set your function f of xy, in this case y minus x squared, equal to c, where c is a constant. And if we do a bit of rearranging, we get y equals x squared plus c. And of course, this is the graph of a parabola. After rearranging, we have y equals x squared plus c. What we want to do is pick 4 different values of c to give us 4 different contours for our contour diagram. So I'm going to start by letting c equal 0. Then we'd have y equals x squared, which you know is a parabola with vertex at the origin that opens up. So I could label this curve the c equals 0 contour. And then I'll choose a different value for c, say c equals 1. We'd have x squared plus 1, which is this parabola shifted up 1 unit, so I'll label that the c equals 1 contour. And the other values of c I'll choose are -2 and -1, giving me these contours. And what you see is the contours become more closely packed as we move farther from the y-axis. So as you're moving left or right, these contours are becoming more closely packed, and you can see that better in this illustration. So here's our surface, z equals y minus x squared, and here's the contour diagram. So you're seeing these parabolas, and this is what I was saying, as you move away from the y-axis, these contours are becoming more closely packed. Here's one last example, and this is the function of 2 variables we looked at the start of the chapter. It's this cost function c that depends on 2 things: the number of days you rent a rental car and the number of miles that you drive the car. So we write c of d comma m equals 40d plus 0.15 m. What we want to do is draw a contour diagram for this function. So again, we're going to be doing some horizontal slices. It says include contours for c equals 50, 100, 150, and 200. So as usual, we set our formula for the function, in this case 40d plus 0.15 m equal to c, where c is a constant. Notice we're told though what we should choose for our values for c. We want to use 50, 100, 150, and 200. But before we do that, let's do some rearranging. I'll subtract the 40d from both sides to get 0.15 m equals c minus 40d, and then I'll divide through by 0.15 to get m by itself. So we end up with this, which is the graph of a line. I'll illustrate how to find one of the contours. So now we're going to let our constant c be 50. Then we end up with this equation, m equals 20 over 3 times 50 minus 266.6d, and it reduces to this. So let's start by finding the intercepts of this line. When d is 0, m is 333.3. And when m is 0, we end up with d equals 1.25. So now we've got our 2 intercepts, which I've plotted here. And we know this is a line. So here's our first contour, c equals 50. We'll use technology to plot the other contours. Here's the image of our surface, and notice it's just a plane. And the remaining contours look like this. They're just these parallel lines. So that wraps up our discussion of contours. I'll see you next time.